Okay, welcome to lecture 4. So the question I was just asked is what is this business of SON inside SON plus 1? So what we did was, just to remind you, that we took a set of fields phi A which transform under SON plus 1. So A goes to from 1 up to n plus 1. So they are n plus 1 fields, and if we take the free Lagrangian, we are absolutely sure that it will have SO n plus 1 symmetry. And now we add a term which also respects the same symmetry, which is phi A minus, what did I call this? Mu squared. So far so good. Then we realize that if lambda is very large, then effectively it imposes a constraint phi A equals mu squared. Instead of saying that, we can just say we feel we are in a mood to impose a constraint phi A equals mu squared. We can just do it by hand. So impose so now we are certainly not going to have the same theory. It's a new theory. The old theory plus a constraint is not the same as the old theory. Just to give you an example, a free particle that's moving in a line, in a plane, I can impose a constraint that it moves on a circle. Particle bead on a wire, people say. Okay, it's not the same problem at all. It was a 2D problem, now it's a 1D problem. Similarly here, it was an n plus 1 field problem. Now it has become an n field problem because of one constraint. In fact, it's more or less the same constraint, because we have constrained the field to live on a sphere, its values to live on a sphere. Now we solve the constraint by picking one of these arbitrarily. And that one that we'll pick by convention, it's convenient to pick phi n plus 1. This is not phi to the power n plus 1, it's the last component of the original phi. We just pick that and we solve for that one, and we find the solution is square root of phi I minus mu squared. That solves the constraint, because this can be broken up into phi I and phi n plus 1 squared. Okay. Yes, maybe the other way around. I think I've been writing this consistently, but it's certainly the other way around. Okay. Now, once I've done this, this equation does not have SON plus 1 invariance. That's clear, because there are n fields on this side and one field on this side. Okay, the original equation had SON plus 1 invariance manifest, but once I pick one and solve it, it doesn't have manifest invariance. We don't see the invariance, but it's there, hidden. We haven't changed anything, we have simply solved this constraint. So the invariance is there, must be there. We didn't do anything to the system. There's no difference between this and that. This implies that, that implies this. But this one, we have lost manifest SON plus 1 invariance because we don't see it. Here we can see it. There are n plus 1 indices and they are contracted. Here, there are only n indices contracted. So the manifest invariance from now on is only SON. And now when we plug this back into the Lagrangian, we'll get a Lagrangian which I wrote last time. And it has manifest SON invariance, but it has true SON plus 1 invariance. Now the manifest invariance, why is it manifest? Because under SON, this transforms by an orthogonal matrix to times itself. So does this, and then O transpose O is 1. That's the reason why it's manifest. But what is that transformation? It's a linear one, because phi I goes to OIJ phi j. So this is linear in phi j. Okay. The missing part, which are n generators which are in SON plus 1 and which are not in SON, they can't possibly act linearly. So they must act non-linearly. And they will act on this guy also. So the point is that they were acting on this guy in the original Lagrangian. But once I solve the constraint, this is not independent anymore. So now they must somehow act on phi I and phi I, so that the Lagrangian is finally invariant. Okay, but how exactly they act, that is a bit complicated to work out. All we can be sure is it's not a linear action. So we say that ON is realized linearly and the rest is realized non-linear. Okay, now any more questions? So today we are going to do the last comments about scalars, and if there's time, which I hope there will be, we'll also start talking about fermions, which present a whole interesting class, fermion fields, which present a whole interesting class of features, some of which are common with these and some of which are special to fermions, which I'll focus on. So first, I want to finish one more model, which is really a cute one. It's called the principal chiral model. You needn't worry about the name, these are all historic names. So the idea here is that we take phi being a Hermitian matrix, Hermitian and traceless. We've done it before. But we do something new now, which is that we define a field G, so phi is a function of x and t. So we define a field G to be e to the I phi. We could put a constant there if we want. I won't do that. It's quite unusual because I'm exponentiating a field. Normally, Lagrangians that you have seen up to now probably are polynomial in the field. They're quadratic, cubic, quartic. I don't think you've seen any Lagrangian which contains an exponential of a field, but now it's going to. It's a new type of Lagrangian, and you'll see in a minute why it's interesting. Okay. Now, given that phi is Hermitian and traceless, what property does G have? Unitary. Very good. So it's a unitary field. We can keep at the back of our mind that it's not the fundamental field of the problem, because the fundamental field is phi and G is made out of it. Or we can just think that G is the fundamental field and it's a unitary matrix. We didn't do unitary matrices before, we did Hermitian matrices. Okay, so unitary have some different features. Now, the interesting thing is that because G is this, therefore G inverse is clearly e to the minus I phi. That's obvious. Okay. Now, we want to make a Lagrangian, and as usual we would like the Lagrangian to have some look of some term which is del mu phi, otherwise we won't know what to do with the Lagrangian. It can have a lot of other things, but we would hope that del mu phi is there because it's the kinetic term. Without that, normal dynamics as we know it can't exist. So now we notice a cute thing. Supposing we consider G inverse times del mu G. This is a very interesting quantity. How will this be expressed in terms of phi? Okay. From your experience with exponentials, you know that this is sort of the opposite of this. So if I multiply these two, I just get 1. And there is a G inverse and G, but because it's a field, I've differentiated it first and then I multiplied by G inverse. Okay. How do I find out what this is? Well, there could be many ways, but it's a bit tedious to try and differentiate the exponential. We can just find out what it is to lowest order like this. We'll say that G inverse, expanding this, is 1 minus I phi. 1 always means identity matrix. You can underline it. Minus I phi plus higher orders in phi. And then I'll put del mu here. And then 1 plus I phi plus higher orders in phi. Yeah. Now on the right side, del mu kills the 1. 1 is just constant. So the first term on the right side is I del mu phi. Therefore, this whole thing, keeping 1 from here and del mu phi from here, we get that G inverse del mu G is I del mu phi plus things of order phi squared and higher. The only way to get a linear term is to pick phi from here and 1 from here. If you pick phi from here and 1 from here, you get nothing because del mu of 1 is 0. And if you pick phi from here and phi from here, you will get phi del mu phi, but that's of order squared. So we realize that this quantity G inverse del mu G is a nice quantity. It's basically the gradient of a field, of a scalar field. And so this gives us a basis to write a Lagrangian. Okay. So how should we do this? Well, to write the Lagrangian, we would like to take the trace of del mu phi, and therefore we are motivated to write L is equal to trace of G inverse del mu G times G inverse del upper mu G. So this is I del mu phi, this is also I del mu phi to leading term. The net result is a minus sign, which I don't want, so I'll put the minus here, then it's positive. Okay, so here's the Lagrangian, and it has this feature that to lowest order in phi, it's just the ordinary kinetic term of Klein-Gordon, and it has infinitely many more terms, necessarily, because if you expand this exponential and this exponential and this one, you'll get lots of stuff. Okay, it's clear that you get a lot of stuff, I suppose. Okay, and this is it. This is the principal chiral model. And now I have to tell you why it's interesting. It's interesting because in some sense, it has double the symmetry of any model that we have seen till now. Because I can take G and I can send it to a unitary matrix called UL times G times the different unitary matrix UR, completely independent. Okay, I call it UL because it multiplies from the left and UR from the right. Remember, G is a matrix, so I can always multiply a matrix from the left and from the right, and I get some other matrix. So this is the transformation which I claim is a symmetry of this Lagrangian. Let's see why it is. So remember, these are constant matrices, so they don't care about the dels. Okay, and now it's almost immediate. G goes like this. So G inverse, given that these are unitary, goes like U dagger R, G inverse U dagger L. So now if I look at this pair, then G inverse picks up this factor, G picks up this factor, but U dagger and U cancel each other. This U will survive here, but now this G inverse will also pick up a U dagger. Okay, and then it will leave a U here, UL. This will pick up a UL dagger, this will pick up a UL. Finally, there will be a UR over there, which in the trace will come back and kill the UR dagger from here. Easy calculation. Okay, so what is the symmetry group of this model? It is SUN left cross SUN, right? These are just labels, but it's SUN cross SUN, much bigger than just SUN. So that's a sort of nice thing. And good, so we've done that. And the model has actually interesting applications, which I'll try to talk about, maybe not today. Now, one interesting thing might come to your mind. You might say, well, why did I take G inverse del mu G and not G del mu G inverse? Okay. If I took that and multiplied with another G del mu G inverse, I would also get a principal chiral model, looks the same. But is it the same model? Certainly one thing is true, that the matrix G inverse del mu G is definitely not the matrix G del mu G inverse. These are not equal. Okay.
Called GG
you could have called GG inverse, but once you have defined it, then you have one model there, and I have another model which I can make with this. Is it a different model? Question is whether they are two different models. None of them will be better than the other, but are they two or are they equivalent? Given that these two are not equivalent, the question is that if I square this, which gives me this, or if I square that, which will give me a new model, is that new model actually new? So this I have left as an exercise for you. Turns out that it's the same model. So trace of G del mu G inverse G del mu G inverse is equal to that one. Despite, however, in spite of this lack of equality, this is true. And in the process of proving it, which you should try because it's also given as an exercise in the notes, you'll encounter various identities between G's and G inverses and their derivatives. Okay, the most important identity is that del mu G inverse times G is G inverse times del mu G minus. Can you see how to prove this? Someone?
Put the whole derivative on G.
Good. You take this to the other side, then it becomes the derivative of G inverse G. But G inverse G is 1, so that derivative is 0. Immediately this follows. This is a nice identity and lot of things follow. But again, the interesting thing is that these two are equal, but they are not equal to del mu G inverse, which itself is equal to G del mu G inverse. So these are two quantities which are equivalent. These are two other quantities which are equivalent, but these two are not the same as these two. But if I put them in a Lagrangian and use cyclicity of the trace, then only the model becomes the same. So there's one principal chiral model. Okay. So this is just one comment, and the details are in an exercise. Now, again we can talk about this manifest symmetry. So, because this model, because of this property above, that G inverse del mu G is that plus a higher order term, this Lagrangian is actually equal to trace del mu phi plus higher order. Okay, that's clear? Okay, but what are the symmetries of this term, trace del mu phi? We've done it. We did it 2 lectures back. Is SUN, how does the SUN act? The symmetry is phi goes to U phi U dagger. So, the symmetry of this Lagrangian that we can see of this term, and in fact all other terms, because all will be powers of phi, right? All will be powers of del mu phi, because I'll be just expanding this and I'll get lots of things, but there'll be many phi's in it. Dels don't matter for the symmetry, and the visible symmetry is just U phi U dagger. If I try to take phi to U left, phi U right, it won't be invariant, this thing. Okay? Because U right from this phi will not cancel U left from that phi. Okay, so the visible symmetry is this, which is just equal to SUN, not SUN cross SUN. So what did we find? It's something very similar to what was asked in the question at the beginning. This time, the full symmetry of the model is SUN cross SUN, as we proved right in the beginning, but the linearly realized symmetry is only SUN. and the rest is non-linearly realized. Everyone looking very baffled. So the same story, exactly. What we can see with the naked eye in this form is only SUN. But it must have SUN cross SUN, because without going into this expansion, we did the transformation and it was SUN cross SUN. Part of it is linearly realized, part of it is not. So now how much, let's do the count, how much of it is not linearly realized? Non-linear part has how many generators? N squared minus 1. The difference between the dimension of, so this I'll write here as SUN cross SUN. So the difference between number of generators of this minus this is the number of generators of one SUN. That doesn't mean it is an SUN, just mean because actually it turns out that this SUN is a diagonal subgroup of that SUN cross SUN. You can sort of see it because we have to do this, we have to make the identification that this U is the same, is just the dagger of that U. So that means this SUN cannot be only that or only that. If it was only that, then you should act from the left. If it was only that, then you should act from the right. But it's acting from left and right in a coordinated way. So it's actually the diagonal subgroup. There's a well-defined concept. When I have G cross G, there's a diagonal subgroup G, which somehow has legs in both the original subgroups. You can work it out for SU2 cross SU2 and try to find the diagonal subgroup SU2, which is very easy to do because with SU2 we have the generators J plus J minus J3. Then you have another set J prime plus minus and 3. Then you can find a linear combination of them such that the J3 of the combination is the sum of the two J3s, and that will be the diagonal subgroup. Okay, so the nonlinear part has n squared minus 1 generators. Okay, and now we can ask the following question. Supposing I take some limit in which all these go away, limit of very small fields phi, or I could have put some coupling constant when I define G as e to the I phi. I could have said e to the I lambda phi and take that lambda very small. Then obviously this is the leading term. Okay, and all the other terms would drop out. But in that case, the symmetry is definitely only SUN. So where did the other n squared minus 1 generators go? In the limit, L goes to del mu phi, the symmetry is only SUN. We can see it with the naked eye, right? If there was any other symmetry like SUN cross SUN, we would be able to see it. But this Lagrangian certainly doesn't have SUN cross SUN. Okay, so where did the other generators go? And you know the answer. I've already told it to you in a different example. So you have to tell me now what it is. N squared minus 1 generators, what could they be? They should be symmetries of this, but they don't make up any SUN, something else. What symmetries does this have which are not in SUN?
Constant shift of.
Constant shift, thank you, excellent. So, constant shift, let's count how many? Shift of phi. So phi is a matrix. There's no other term, remember, there's no mass term. And by the way, a mass term would have violated SUN cross SUN. So it's not there right from the beginning. And we can send phi to phi plus some alpha, which has to be a matrix of the same form as phi. Except phi is a field, alpha would be a constant matrix, which we are allowed to shift by. But since phi is a Hermitian traceless field, this must be a Hermitian traceless matrix. Okay. How many components are there in a Hermitian traceless matrix? N by N matrix. N squared minus 1. So we are done. Okay, so again what has happened in the limit where we made this reduce to only this term without the other, whatever manifold this model was living on, this is actually secretly a nonlinear sigma model, just that we can't see it very explicitly. Okay, it's not written in the form G ij del phi I del phi j, but it can be. How would you do it? You can think about that. It's very easy. Okay, you just insert here G is e to the I phi, G inverse is e to the minus I phi, and then perform the derivatives and you will get infinitely many terms, namely this plus dot dot dot, whatever are the dot dot dot, you know that they can only have two derivatives in them, del mu, because this had only two derivatives, right? So any term which comes by expanding it will have only two derivatives. So take out the two derivatives del mu phi, whatever multiplies it is Gij. It's little more complicated because phi are here written as matrices. So we can use the basis of SUN, the generators Ti of SUN, to go to the component vectors phi I, which I showed you once, and then you will find a nonlinear sigma model form. And some details are given in the notes. Okay, but the important thing is that, as usual, we have a sigma model, and when we flatten the manifold by going to some limit, then the model has some non-trivial rotation type generators, namely the diagonal SUN, and the remaining become axionic shifts. So this is the axionic shift. You may actually learn something about axions from Arun's advanced particle physics course, and you'll be able to understand then why it's called axionic. One way to see it in simple language is axionic shift is always there when the theory depends only on derivatives of the scalar field and not on the scalar field explicitly itself. Okay, that's when you can shift it by a constant, because any derivative of phi doesn't care if I shift phi by a constant. So axionic shifts arise in field theories where there are fields which only couple through their derivatives. And this is an example, but it's a trivial example because these are free fields. But you can have interacting fields which do the same thing. Okay? Anything unclear in what was this?
Why the constant shift has to be Hermitian traceless? Why can't we?
Because otherwise it can't be a symmetry, right? Phi is a field which is Hermitian traceless. If I shift by something else, then the after shift it's no longer Hermitian and traceless. So I have to always shift within whatever field I started with. So for example, if I have a real field, I can't make a complex shift of it. It's the same thing. Hermitian, remember, always is the analog of real for a complex matrix. It's like restricting complex matrix to Hermitian is like restricting a complex number to be real. In fact, what it does is it makes the eigenvalues real, which is what real should mean for a matrix. It doesn't mean all the matrix components are real, that's too strong, just the eigenvalues are real. Good? Okay, and one last comment is that there's a cute other way to write this Lagrangian. This happens to be equal to trace, I think still minus, of G of del mu G inverse del mu G. Out of these four things, we got rid of two of them somehow. It's very easy calculation. I think this is with a plus. In fact, I'm sure it's with a plus, though I've written the wrong sign in the notes. I'll correct it before I post the notes. Okay, and this form is useful. Can you see how this comes? Anyone can see it readily? I already gave you an identity which will immediately prove it. I told you that this times this is same as minus of del mu on this times that. Okay, but then once I do that, then G and G tilde, G inverse will kill each other. Wrong place. And I'll get del mu G inverse, del mu G, and the sign will change. Over. Okay, and you can also see directly that this is del mu phi squared at leading order, because this is e to the minus I phi, this is e to the plus I phi. When I expand them, minus I plus I will cancel and I'll get del mu phi, del mu phi. It's very easy. And with this I can also get the equation of motion. So the equation of motion is tricky because I have to vary G, Euler-Lagrange equation, but I have to also vary G inverse. So given variation of a matrix G, I have to work out what is the variation of G inverse. It's not independent. Okay, there is some hint given how to do that in the notes, but eventually you will get the equation of motion del mu of G inverse del mu G equals 0. And there's lots more one can say about this set of theories, but I'll stop on this point. I'll stop here and I'll ask you to read the notes. By the way, there's one class of terms that I can add to a principal chiral model which are called topological terms. I felt that it may be a bit taxing for some of you to learn that right now. So I put it in the notes, but it's clearly marked as optional. So you can read it if you want. And by the way, the rest of the notes which are not marked as optional are all part of the portion of the course, even if I didn't discuss everything in the class. So you really must read the notes. There are a few things which I haven't discussed or haven't derived, but they are all in the notes, and if it's there, then it's in the, it will come up in the quiz or the exam or anything, but not the optional part. Good. Now, two more little points to make about scalar field theories, and we are finally done. Any questions on this? There's a lot of silence going on here. Is it very mysterious? What is the, is new I understand, it's conceptual, that also I understand. Probably, I hope, you didn't expect that scalar field theory has such a richness of structures and symmetries, but they have been very, very influential in particle physics in writing down effective Lagrangians. So it is important. Sometimes we write down effective theories just knowing their symmetries and writing the simplest theory, and actually that's how this originally came about. So people wanted a theory that's invariant under SUN cross SUN, but of which only SUN is spontaneously is sort of realized, is linearly realized. Okay, and this turns out to be the solution to that question. You may read about principal chiral model. There are Wikipedia pages. Don't scoff at Wikipedia. At least on physics, it's usually not too bad. On world affairs, little bit less. But anyway, okay, good. Now, to summarize, we took the basic free theory and we generalized it in two ways. We added a potential, or we made it a sigma model. And these two ways consisted of taking del mu phi, just for example, I'm taking a real field. So either I can add a potential, including the mass term in that, or I can multiply this kinetic term by something. But we saw that with one phi that doesn't work, it's trivial after field redefinition, but with multiple phi's we'll be able to do that. And that's this, so adding this is the first way, and putting a metric here is the second way. Okay, now is this all the ways that we can make life complicated? No. So there's one last interesting way, which is called, which doesn't start from this at all, and it's called higher derivative terms. And as the simplest example, let's write this theory, which we are very familiar with, and then add to it a term Yeah, could you please talk somewhere else? Yeah. Okay. So what can you say about this? Like it? You don't like it? Let's have a vote. Who likes it? Who doesn't like it? You know, in my generation, we used to have opinions on everything. Mostly we were wrong, but that's better than having no opinion. Yeah.
So in this Lagrangian, we can't like use our normal equation of motion.
Exactly.
Right?
Absolutely. What is the equation of motion? Thank you. So the equation of motion, let's put a constant here just to, there should be some limit when this theory goes back to what it was. So we'll actually consider this with some alpha here. We'll also allow a potential. We'll also allow a mass term, or we can include it in the, no, let's write the mass term separately. Thank you. Your comment was absolutely right, and now we'll see what it is. And we can have a potential also. Okay. So the first observation is, assuming the potential starts with phi cubed, because the phi squared term in the potential is written out, then all this stuff in the beginning is all of order phi squared. And that's the operator that we are supposed to invert to find the propagator. We have to go to Fourier space and write the thing that multiplies phi squared. We write phi, some operator phi, and then inverse of that phi is the propagator of the particle. Okay, good. So first of all, let's write the equation of motion. So the equation of motion from this is del mu phi plus 1 by alpha del mu squared. And phi, actually we don't have to keep writing phi, we just write the whole operator, and then minus m squared phi minus, m squared, all this on phi, and then minus v prime phi. That is the first derivative of v with respect to phi. This has to be equal to 0. So this is the what is called the kinetic operator. If alpha was infinity, then it would be the Klein-Gordon operator, box minus m squared, but now it has a new term. Okay. Notice that for the first time, we have added something which changes the free part of the theory. Until now, we were only adding things which change the interacting part of the theory, the higher terms. At the free level, all our theories were familiar del mu phi, with or without a mass term. But we were adding possible interactions. Now we've added something which actually isn't an interaction because it's quadratic. Is this obvious? By the way, people are puzzled. I hope from QFT1, one of the most important lessons you took away is that the quadratic part of a Lagrangian is the free non-interacting, describes free non-interacting particle, because the equation of motion from that is linear. When an equation is linear, then superposition holds and the particle doesn't really interact with anything else. Okay. So though quadratic is not same as linear, but in Lagrangian, quadratic means free. In equation of motion, linear means free. Okay, good. So we have this thing. And now from this operator, we get what is called the dispersion relation, which normally, without this term, was p squared equals m squared. This is the Einstein relation, where p squared is e squared minus p3 vector squared is equal to m squared. That's, or e equals square root of p squared c squared plus m squared c fourth, if you like mugging things by heart. But c is 1. So this is the normal dispersion relation, and that comes by going to a Fourier basis where del is replaced by minus I times p. Okay, so now if we do the same thing, then we get a dispersion relation, which is, I have to correct a few signs in my notes, but not very important. So the dispersion relation now is p squared now I've done something wrong. The Klein-Gordon equation was with a plus, no? Box plus m squared in my conventions. Yeah. So p squared minus p to the minus 1 by alpha p to the fourth. I keep m squared on one side, take everything else to the other side, where this becomes minus of this becomes plus p squared, and that thing just becomes p to the fourth. with a minus sign. So this is equal to m squared. Okay. Now this kind of thing is a polynomial in p squared. So I can factorize it, and the details are not very important, but it will certainly factorize into the form p squared minus a1 p squared minus a2 equals 0. Any polynomial can be written that way. But now we see that we have a couple of problems. First of all, this doesn't seem to describe one particle satisfying p squared equals m squared. At best, we could say it describes two different particles, one satisfying that p squared is this, where a1 is the square of that particle's mass, and then another particle where a2 is the square of the other particle's mass. So it has double the number of poles in the propagator. Twice. Normally the propagator has a pole because it's 1 over p squared minus m squared. When the particle is on shell, the propagator has a pole. But this has twice as many poles. So it's totally a new thing. Okay. So it seems like we have two types of particles, but it could be worse than that. It may be, depending on this alpha, that these A1 and A2 are not very nice. They might have the wrong sign, or they might be complex. A lot of things can happen. Okay. So it is tricky, and I don't want to pursue it, but I just wanted to show you that here's one model with higher derivative interactions. But because those higher derivative, what is higher derivative? 1, 2, 3, 4 derivatives. Okay, but still acting only on two fields. So because of the nature of this interaction, this thing doesn't rather doesn't have the usual dispersion relation p squared equals m squared. That's the point. Yes.
Sir, Lagrangian with q dot and q double dot. There is a problem with that. Right?
Yes, it's similar to a, thank you. It's similar to a Lagrangian depending on q dot and q double dot, and actually it does, because when all these mu nu are equal to t, then this is phi double dot square. So it's exactly similar to that. Yeah. So this will have similar problems. So this will have unboundedness problems. Thank you. You can work out the Hamiltonian and convince yourself. So there are problems. Now that, often these problems mean that people give up working on such theories, but then people find sometimes that, well, the problem is cured if I don't stop here. Supposing I have this and then del cubed phi, and I go on to infinity, then sometimes the theory is a little better. So there are still papers. People are still writing papers on these higher derivative theories, and it's a sort of open question. Okay, ultimately, it is what you need it for. But I'll just mention that we can't avoid them because of something which I'll discuss later in the course, which is the Wilsonian approach to deriving effective field theory. So just words that I'm not going to go into detail. Supposing I take a theory and I integrate out, as it were, the massive particles to get a low energy theory. This is very commonly done. When I do that, I tend to get all possible derivative terms. So in the effective theory, I could have this. And my problems could be solved by saying that, well, whatever bad behavior the theory has is explained by the fact that I integrated out some other degrees of freedom which should have been there. Sometimes when I do that and I then extrapolate to some energy scale which I'm not supposed to go to, then I can run into these problems. So just to say that when a Lagrangian seems to be inconsistent, or equations of motion seem to be inconsistent, we don't necessarily throw them in the garbage. It definitely discourages people from doing certain things, but we should be prepared that they may come back in some other context. In field theory, almost anything bad you do will come back in some other context as a good thing. It's very strange, but it's true over a very long period. So we should be prepared for it. That's why I wrote this. But now I'll write for you one more higher derivative Lagrangian, which has a completely different property.
Sir,
Yes.
these dispersion relations which might lead to like these multiple poles.
Yeah.
Is there any physics in context of particle physics, let's say, associated to like can is this realized physically, or are these?
Yeah, my feeling is that it's realized physically only in effective field theory, where you should not take the multiple poles seriously. but I have to check, and I haven't thought probably too much about it recently. So, but I can let you know when we can discuss it. Yeah. Okay, so here's a different model. That was one model of a higher derivative Lagrangian. Here's a different model, and it's inspired by old work of Dirac and also of Born and Infeld. But their work was in the context of electrodynamics. And we'll discuss this again when we do electrodynamics, when we do gauge fields very soon. But you can take that inspiration and write a scalar Lagrangian, which I'm pretty sure they did not do, which is the square root. This is already interesting to have a square root in a Lagrangian, then a mod of a determinant of the following matrix: eta mu nu plus del mu phi with a constant in front. Actually, yeah, I could put a constant. Probably I'll put a constant and I'll put the same constant here. You'll see why. Mod. That's the Lagrangian. So we don't even contract these indices. It makes a matrix, and I add it to the identity or Minkowski metric, and then I take the det of that, and then I take the mod and the square root, and I have a Lagrangian. Well, it's an easy exercise to show that if you expand this, the first term is half del mu phi. You see, everything is rigged up to give you half del mu phi as the leading term. What's the next term? Well, in this case, you can work it out. It will have an alpha. So, first of all, there'll be a term which comes when alpha is 0, alpha independent term, but which will have 1 by alpha, but it will be just det of eta, and that's just a constant. So, constant we can always drop from a Lagrangian, additive constant. So, that we don't even write. The next term, if you don't like that constant, you can always subtract it here, like this, in the definition. Then the constant will go away. Then you get this term, and we rigged it up so that this comes with an alpha, this comes with 1 by alpha, they cancel. The square root gives you the half, and this is the correctly normalized free real Klein-Gordon field. The next term will be with alpha, and it has del mu phi whole square minus del mu phi whole square, and then it goes on forever. Now, what's the key difference between this and the previous one is that the dispersion relation does not change, because all these terms are of order not only higher derivative but also higher powers of phi, because the way I wrote it, every del comes with a power of phi. Okay, so that's very nice. So dispersion relation is normal. So this we should be happy at the free level. And these are all interaction terms, and there are infinitely many of them. So this kind of action generically goes by the name of DBI for Dirac, Born and Infeld. But what they did was a little different. Here, instead of scalars, they put F mu nu here, the field strength of electromagnetism. And then you can do the same thing. It's also gauge invariant, and it's an interesting action. Okay. Now in the last 5 minutes, any questions about this? So I do have 5 more minutes.
Sir?
Yeah.
Usually when we are trying to quantize the theory, we usually prefer not to have square root sort of Lagrangians, right? So if you want to quantize this, would you always consider this as a power series?
Yeah, so it's very hard to quantize, because actually technically the correct statement is that these are higher dimension operators and it won't be a renormalizable theory. But this kind of discussion is for the last part of the course, and the separation is important to me, because this classical field theory where no such problem arises, We're just trying to think whether it may make sense when we quantize it. And sometimes it doesn't, sometimes it does, and sometimes it's in a gray zone where it makes some sense as an effective theory. Very commonly in string theory, these things arise as low energy effective actions. That's why there's been recent interest in it. But even if you are not interested in string theory, it's very clear that in gravitational theories, the only thing we know about Einstein action is at small values, at low energies, at small values of the momenta, which is like low values of del mu, because del mu in Fourier space is a momentum p mu. Okay, so when you have a strongly curved, a highly curved space-time, then such terms could be present and they would make a difference to your physics. And it's widely thought that in general relativity, Einstein's theory is only a lowest derivative, two-derivative approximation to a much more general theory, a low-energy theory. And actually it's the same logic here. But in GR, it's actually interesting to people also who don't necessarily take the inspiration from string theory. Okay, I really want to finish Boson's scalars today because I'll start on a new thing next time. But if I don't have time, I have like 7 minutes, I will let you finish the rest of it. So, this topic is called Euclidean continuation. Now, as you know, we normally write our space-time metric as 1 minus 1 minus 1 minus 1, and we work with this, and that's because space and time are really different things. However, there are two problems. One is path integrals have bad behavior oscillatory behavior due to this metric. The second is there are statistical systems which are not quantum systems, live in Euclidean space. For example, if I have a magnet, then it will live in a bulk system, with magnetic system, then it will live in 3 Euclidean dimensions. But the continuum limit of that, so it's a crystal, so actually all the spins are separated from each other. But there are some situations, typically at a phase transition point, where you can go to a continuum limit and try to describe your magnet by a continuous 3-dimensional theory. Now that continuous 3-dimensional theory has many properties in common with 2 plus 1 dimensional quantum field theory. Okay, but the physics is completely different. The manipulations are very similar. Okay, 2 plus 1 dimensional quantum field theory describes 2 space dimensions and time evolution. A 3D system doesn't have, statistical system doesn't have any quantum interactions. It's all classical. I mean, we're talking of classical 3D systems, spin-spin interactions and all. Okay, they may be quantum ultimately, but we are treating them as a statistical system with some probabilities, some Boltzmann weight for different configurations. So that system, the dimensions are all on equal footing, but the way it behaves is governed by the way field theory behaves in the space-time. And so by doing this continuation, we'll be able to take a field theory and go to a statistical system. Now, if we do it in this theory, we'll go to a statistical system that lives in 4 space dimensions. That doesn't exist, but we often do lower dimensional field theories, and we'll be able, and it's been a very rich subject in condensed matter physics. So this is what is called statistical field theory. For both of these, we need Euclidean continuation. And to make the story very short, all we want to do is take t and replace it by plus or minus I tau, and then take tau to be real. Okay, so t starts to behave. So we just treat t as if it's imaginary, t being the time coordinate. We formally do it. Now I want to emphasize that this is a minefield. You can always mess up lots of things. Okay, but sometimes you improve things. So for example, if you have a behavior like e to the I alpha t, then after this continuation, it will go to e to the plus or minus alpha tau. Supposing I wanted to integrate, this integral is miserable, it just keeps oscillating. This integral is very nice if I have the minus sign. It's bounded now, it's decreasing, damped, wonderful. With plus, it's horrible even more than this was horrible, it's worse. That means that only one of these signs will work, other one won't work. Okay, but it can be a good thing to help us make integrals converge, and this is why we use it in path integrals. Now the only significant thing to remember is that if I do this here, effectively eta will become minus 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 minus. But the metric of Euclidean space is plus 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 plus, not minus 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 minus. So we need to have some rules to map the Lagrangian to a Euclidean Lagrangian, and here's one example. So, and with that I'll stop. If I take del mu phi, this is phi dot squared minus grad phi squared. If I now go t equals minus I tau, which turns out to be the good one, then I'll get minus del tau phi squared minus grad phi squared. And I don't want to call this my Euclidean Lagrangian because it's negative rather than positive. So I'll say that the Euclidean Lagrangian is minus of whatever I get from the original one by sending t to minus I tau. That's the key point. And it has another advantage. If there was a minus v here, it would become plus. So the Euclidean Lagrangian is all positive terms. Unlike the normal Lagrangian, which is t minus v, the t becomes negative, then we add a negative sign by hand and everything is positive. So Euclidean Lagrangian is always greater than or equal to 0. More details are in the notes. Okay, questions? I think we should get out of here now.